Good day. I hope you guys are having a good morning. What I want to do is just walk you through this document to help you get through it. So here we go. We talked about this a little bit yesterday, and there's two situations. Cindy and Victor, they're playing the game. They're trying to line these up in different sets, number sets. Victor says that he's lined them up in positive numbers, whereas Cindy lined them up as rational numbers. Well, technically, they're both correct. Technically, they are both correct, but Cindy is more correct. More correct because she's actually using a specific number set that we're going to turn around and talk about a bit before. But she is definitely more correct than Victor. But Victor again is not wrong. It's kind of like the fact that, like, if you owe me $100 and you gave me $100 bill, and then or versus you owe me $100 and you gave me $100 worth of pennies, you're both correct, but I would much prefer the $100 bill over the $100 in pennies, like, because that's just not right. That's just not cool for the $100 in pennies. Anyway, so there's 5 number sets. To talk about this, when you looked at this a little bit yesterday with the real number system, we kind of expected you to take that and Google that and look up what that actually is and see what Google or see what some internet search would provide. Ask the person next to you, because that is a definition that you can really know yourself and figure out on your own. But if you don't do that, that's totally cool. But whenever there's vocabulary, definitions, and questions and words that you don't actually know what those are, you can just jump on a search engine, type those words in, and see what happens. If you see a definition that you don't get, let us know, and we can absolutely clarify that for you as needed. Anyways, so these number sets are actually easiest described by an image and starting from the most restrictive number set that we know of. So if I skip down here and we look at these two images, the lowest, like, most restrictive number set we talk about are called the natural numbers. The natural numbers, those are more also known as the counting numbers, but that's technically not their fancy name. Natural numbers is their fancy name. That's like the numbers 1, 2, 3, 4, and so on and so forth on forever. One more step kind of above that, which has one extra description, are called the whole numbers. The whole numbers are defined as the natural numbers, including the number 0. Okay, so that's 0, 1, 2, 3, and so on and so forth. Up above that, kind of a little bit more broad in spectrum, are called the integers, because the integers are defined as the whole numbers and their opposites. By opposites, we actually mean negatives. So that's like -2, -1, 0, 1, 2, 3, 4, and so on in that direction, and so on in this direction. All 3 of those are part of the rational number system, which is a little bit broader. So rational numbers can be defined as the integers, or rather, any number that can be written as a fraction or division problem of integers. So -1/3, 1/2, 8 with a whole bunch of zeros over 3, if you want, so on and so forth. These, some descriptors of those can be non-terminating decimals, but if they're non-terminating decimals, meaning decimals that don't stop, they have to repeat. Which leads us into one more set, irrational. Spell that right. Irrational numbers. Okay, those are anything, any number that cannot be written as a fraction of integers, or any number that you know that can't be written as a fraction, or has non-terminating, non-repeating decimals. So like 2, pi is a pretty popular one. There's a letter E, things like that. Those 5 sets make up what's called the real number system. Now, while they're drawn in relative size here, this picture is really just meant to show which ones are part of the others. So for instance, these rational numbers and irrational numbers are both part of the real number set, but they're not, one isn't necessarily larger than the other per se, as the picture describes. These are more, this is a little bit more telling in that this represents that you have the most broadest category, and then there's subcategories down below. Okay. There's another one here that talks about all numbers. There's one called the imaginary. These are called real numbers. There's another one called imaginary numbers. If you have heard of those, that's pretty fancy and pretty neat. But you likely haven't used those or heard of those or operated through that yet. Anyways, so here's another question that talks about us reasoning. Can you make other groups using the numbers shown that are all the same kind of real number? Same kind of real number. That means a subset of real numbers. One of the subsets that we just talked about. In how many ways can you do this? So, for example, Cindy could take -5 and put that right there. Okay, and then these 3 right here, those would all be represented by rational numbers. Okay, so there's one. You could do another set. Let's say Victor takes 3, or you know what, let's do negative or square root 8. He could take that and put that here. And then these 3 would then be represented as irrational numbers. So on and so forth. There's more examples if you want to think through that. Cindy says that 1/3 is an irrational number because the fraction form doesn't terminate. Construct an argument to support or refute Cindy's position. So yes, the decimal, if you remember, or if you divide it in your calculator, is going to be 0.3 repeating. So it's going to go 0.3, 3, 3, 3, 3, and on for infinity, as many as you feel like writing down. But the issue is, that's not what makes an irrational number. What makes an irrational number is the fact that you can't write it as a fraction of integers, whereas 1/3 is in fact 2 integers, the integer 1 and the integer 3. So it would be more specifically referred to as a rational number rather than an irrational number. Irrational numbers, again, are numbers that do not terminate and do not repeat. 2 examples of sets that do not contain numbers. So this could be a wide open thing. It could be you have all of the trees that exist in the world. Okay, so that would be the parent set, for instance, and a subset of that would be the North American domestic trees. Now, for example, you probably don't know this, but there's a wood called parawood. There's the parawood tree or the rubber wood tree. That is local to Indonesia. It doesn't grow here. Okay, that would be a member of the trees that exist in the world, but it would not be a member of the trees that exist in North America. Black walnut would be a tree that does not grow in Indonesia, but it's still a tree of the world, and it does grow in North America. So the set of numbers from 1 to 10 are both subset of odd numbers and the subset of multiples of 3. So now you could do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You might think that those are all the numbers that we're talking about. What we're really talking about additional numbers like pi, okay, like square root 17, probably in there, that's a guess. So yeah, it's in there. It's actually more closer to 4. Anyway, so square root 17. But which ones of these are odd numbers? These are the only odd numbers that are represented, so that qualifies for that. And then if we want to also multiples of 3, find the multiples of 3. That's not a multiple of 3. This one is. That one's not. That one's not. This one is. So the answer to this would be 3 and 9 is our answer. Given set of numbers, which elements are both in the set of numbers divisible by 2 and the numbers divisible by 3. So numbers divisible by 2 would be 6, 8, 10, 12. Numbers divisible by 3 would be 6 and 12. So just those two guys. Determine whether the set B is a subset of A. So you'd start looking at B. You have two numbers, 1 and 2. Are those two numbers represented in A if it's a subset? So all of those numbers then have to be in A. So A, do we have a 2? Yep. Do we have a 1? Yes. So we would say yes, B is a subset of A. Draw a smiley face for fun. Give an example of two sets of numbers where one set is a subset of the other. Use what we learned before. We could use the rational numbers to be a subset of the real numbers. In what other areas are sets and subsets represented outside of mathematics? So classifications, essentially same thing as what I responded to up above with the trees. Mr. Suter suggested that you could do the GHS baseball would be a subset of GHS students. Approximating irrational numbers between which two numbers is square root 12. So what do? Is we can look for perfect squares if we do it without a calculator. You can do this with a calculator if you want, but we're kind of guessing without a calculator. So think of perfect square numbers like 1, 4, 9, 4 squared is 16, 5 squared is 25. So which two of those is 12 in between? It's in between like 9 and 16. So then square root 12 would then be in between square root 9 and square root 16. Square root 9 is 3, square root 16 is 4, so 12 has to be between 3 and 4. So going to order these from least to greatest. So you could do it without a calculator. You kind of have to guess which numbers they're around. So this is 1.2. That is like negative 2 times pi. Pi is like 3.14, so it's like negative 6.28-ish. That's negative 3.5. This one might be hard, so we got to think of what we did up above. What two perfect squares are around 6? So we had 4, and we had 9. 6 would be between those. So square root 4, square root 6, square root 9. So it would be 2, square root 6, 2, square root 6, and 3. So that's somewhere between 2 and 3. So if we slide these in order, it would be the super negative number, the most negative, then the next most negative, and then one that's between 2 and 3, that's more than 1.2. So we would write 1.2, and then we would write as the last square root 6. You could drop it in a calculator if you wanted to. So same thing in this. I would probably suggest either get a common denominator here or drop it in your calculator. Get it through. Denominator, we can multiply this one by 16 over 16 and this one by 4 over 4. we would get 16 over 32, 15 over 32, and 20.